Okay, like I said, we're going to turn the corner now in calculus and see how calculus applies to something different. We've seen how calculus applies to slope, rate, things in motion, rates that are changing and maximizing and optimizing. That's one branch of calculus. That is called differential calculus because it's all based on derivatives. So now we're switching gears and we're going to switch to the other application of calculus, which applies to the finding of area and what that can tell us and what we can learn about functions by knowing their area. So the need arose to be able to figure out the area of a particular function. Now the Greeks, remember, the Greeks could do in the area of anything that had a straight side to it. If it had a straight side, they could figure out the area, or if it was circular or elliptical. But if you gave something that was irregular in shape, that had an edge defined by a function, then the Greeks really were stuck. So the best that they could do was subdivide this into a fixed number of intervals. So this is an approximation approach. And what the approximation approach would do was to use a finite number of intervals. The greater the number of intervals, what would happen? More accurate, right. Okay, the fewer number of intervals, the easier the math, but the worse your approximation was. Now we're going to cover 3 different kinds of intervals. So either the top of your interval could be a straight line, which would make a rectangle. So either we're going to look at rectangles, which if you made the top of your interval a rectangle, then you could see how much error you were going to have, that great big gaping, like triangular sort of shape. The next best thing was to make the top of your region an oblique line, which would then make a trapezoid. And if you do the trapezoid, then your error went way down because now your error is just, that tiny little sliver. And finally, the best approximation before calculus that anybody came up with was, I want to pick this color, okay, was a curve paraboloid. And that is named after the guy who did it, which is Simpson. Okay, Simpson's method. And his still had a tiny bit of error to it, but it was pretty darn close. It wasn't until Leibniz came up with the use of calculus that they were able to eliminate error altogether. And so you started simple with rectangles, moved on to trapezoids, and then paraboloids. And each time, the error decreased and the accuracy increased. So I've preloaded those programs onto your calculator already. There's a program for RAM, which is the rectangular approximation method. And so I'll color code them. Okay, rectangular approximation. There's trap. Oops, that was yellow. Okay, there's trap, which is a trapezoidal approximation. And then there's simp on your calculator, which is parabolic approximation. Ram and trap, you probably will have to do by hand at least once with a small finite number. Simpsons, you won't usually ever have to do that by hand. You'll be able to calculate that using the program. So what I'm going to do with you is practice a ram and a trap for the same problem. We're going to do the same question 4 times. LRAM, RRAM, MRAM, and trap. And we're going to see how our accuracy improves each time we do it. Okay, so what we are going to do by hand is this. We're going to do the parabolic function f of x equals x squared minus x plus 3 on the interval from 0 to 3 using 3 intervals. So we'll keep the math pretty simple. So it's a parabola, 0 to 3, and we're going to do 3 intervals on that just to keep the math easy for us. Okay, here is what the function looks like. From 0 to 3, divide that into 1 to 2. And I've already done the math on this to prepare. And so the coordinates are 0, 3, 1, 2, oh, shoot, my scale is poor. Yeah, my scale is poor. Shoot. Okay, well, we'll have to use our imagination. 2, 5, and 3, 9. Here, how can I fix that? Let's see. I could do this. A little bit better. Still not great. All right. So there are 3 kinds of rectangular approximations. So go ahead and draw the vertical lines that will create the subdivision. And we're going to start with L. Now when I do an LRAM, I'm only going to use 3 out of the 4 points. Yes? Yes. That's why my graph is off. Okay. Okay, LRAM. We're only going to use 3 points. Which point are we not going to use for LRAM? 3. 3, 9. We're not going to use LRAM for 3, 9. Okay, so as we draw our going from left to right, this one happens to go straight across. The next one will go straight across and then straight across. So I actually will have, in this case, 2 rectangles of equal height and 1 rectangle that's a little bit taller. And so we're going to determine, using our LRAM, the base times height for each of the 2 rectangles. So we're going to have an area of 3, and an area of 3, and an area of 5. 3, 3, 5. So our LRAM value is going to be 11. Okay, for RRAM, we work our way from right to left. This time we will not use 0, 3. So this will be an overestimate. So working our way from right to left, I have rectangles that are all distinctly larger. So this is going to be an overestimate. Because this is an increasing function for the most part, there's a tiny decreasing section in the interval of 0 to 1, but overall this is an increasing section. When you have an increasing function, the LRAM will always underestimate, the RRAM will always overestimate. Okay? You do not use concavity in this case. For RAM, you only look at the increasing or decreasing nature to tell whether you're going to over or underestimate. All right, so my my RRAM is going to be 3 again, then 5, then 9. So my RRAM will be 17. Yes?
Can you say what you said again about the increasing and decreasing functions?
Mm-hmm. If it's an increasing function, or for a majority, it's an increasing function, LRAM will always underestimate. And RRAM will always overestimate. If it is a decreasing function, then that will be the reverse. For a decreasing function, LRAM will always overestimate because the left side of the interval will always be higher on a decreasing function, therefore leading to an LRAM that's higher. Okay, is MRAM just the average?
No.
No. Okay, MRAM is not the average. MRAM is the midpoint. And so I have calculated these for you. Okay, these 3 midpoints. Okay, and I'm going to zoom in. And the midpoint is 0.5, comma, 2.75. The second midpoint is 1.5, comma, 3.75. And the last midpoint is 2.5, comma, 6.75. And so that will give me, sorry, I'll zoom back in so you can see that. Okay, so it was 2.75, 3.75, 6.75. And because the bases are all 1, so at the midline then, I draw the height. And that's going to give me a much better approximation because at the midline, it's partially under and partially over the curve. And so my MRAM is the addition of all of those heights. So it's 2.75 plus 3.75 plus 6.75, which is 13.25, which is going to be the best accurate equation so far. All right, so last one we're going to do is trap. For trap, what's interesting about the trap of the first one? It's still a rectangle because those happen, for trap you connect the endpoints. And so for trap I'm still just going to be going straight across. But for my other ones, trap will connect the endpoints here and trap will connect the endpoints here. For trap, you do look at the concavity. And you can tell, you predict that this will overestimate it slightly because your oblique pieces that are connecting the top of your trapezoid, the concavity of the function causes the function to actually fall right beneath that. And so that's going to overestimate. So with our LRAM right now, we have our LRAM being an under. We have our RRAM being an over. Our MRAM is, we can't predict really either way what it is. And then we have our trap. And our trap is going to be an over again because of the concavity. So with LRAM, you use the direction, the increasing or decreasing nature, to talk about whether it's over or underestimate. For trap, you use the concavity. Okay, so let's do our trap. Trap is going to use the formula 1/2 of the two heights added together times the base. So that'll be 1/2 of the two heights, which were 3 and 3, and the base was 1. So that's pretty boring math. I picked it because it was easy. And then 1/2 of the two heights added together, which are 3 and 5, and the base is 1. And then the last trapezoid is 1/2 of 5 and 9, and again the base is 1. So that trap turns out to be 14. But remember, 14 is just a slightly over. And so our best estimate here is it's going to be somewhere around 13.25 and 14. We know that 14 is going to be slightly over. So it's somewhere between 13 and 14 is the exact answer. And the only way without calculus to improve on that would be to subdivide these regions again. Yeah? 3 plus 4 plus 7. 3 plus 4 plus 7? Okay. Okay, let's run simp. We'll do that on our calculator.